We're going to continue our discussion for Chapter 5. This is our last section. We're going to talk about orbital diagrams. And we'll also talk about valence electrons and dot structures as well. So orbital diagrams or orbital notation is a way that we can draw our electron configuration and show the individual electrons. Remember that they have opposite spin. So on your quantum numbers sheet, this would have been, N would have been 1, S would have been, our L value would have been 0 for the S orbital, and then we would have had 0 for our M number, and then we would have had a plus and a minus for these. And so when we get over to like the 2p section here, this one would have been your -1, this would have been your 0, and this would have been your 1. And then if you look at the p over here for 3p, this would have been a plus, 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 and this would have been your first minus. So this is what we're talking about for orbital notation. This is of sulfur here. When we're doing these, again, we use our blanks to represent those arrows, and we do them in a certain fill order. So up, down, then we went up, 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 and then we would go down again. We don't pair up electrons until we have one placed in each orbital. If we do that, then we're violating one of the rules that we talked about when we were discussing electron configuration. So when you do anything in the S block is going to get one blank. That's for the 0M number on your quantum numbers periodic table. The P block will get 3 blanks, one for the -1, one for the 0, one for the 1. D block gets 5 blanks. And the F block will get 7 blanks, whether you use them or not. If you may not have enough electrons to fill them all up, but they still all have to be there. So let's look at silicon. Silicon is right here on our periodic table. Remember when we're doing these that our helium is over here, as opposed to our traditional periodic table that has it over here, but we want it nicely placed in the S block. So we are going to work our way over to silicon here. This is our goal. So we always start back with kind of our chutes and ladders idea, where we start back at 1. This is our N number here is 1s. We need both electrons. And I'm going to do the electron configuration first, and then we're going to go back and do the orbital diagram. So this is 1s2. Then I go in numeric order. This is 3 and 4. So the N number here is going to be 2. That's 2s. We need both electrons, so 2s2. Then we go over to this section here. This is our N number here is 2. Now we're in the P block, and we need all 6 electrons. Then we go numerically down to 11 and 12 here. So this is 3s, and we need both electrons. And then we're going over to silicon. So here we are where our N number is 3. We're in the P block, but now we only need 2 electrons. So this is going to be 3p2. Now we're going to do our orbital diagram. So our orbital diagram for this, we're going to do, anytime we have an S, we do 1 blank, and then we put that underneath it. Our 2s is here. 1 blank again because it's an S. Our 2p, P's get 3 blanks. So our 2p is here. Then we have our 3s. And finally our 3p. And then we use our arrows to represent these electrons. So 1, 2, 3, 4. Remember, when we get over to the p's, we always put them in 1 in each orbital first, and then we double up. So it's kind of like cars. Okay, if you have a 3-seat car, you're not going to have anybody sitting on somebody's lap until each person has a seat filled. Then our 3s, we have our 2 electrons here. And again, we've got our 3-seat car. They're not going to sit on somebody's lap here until all of these seats are filled. So that's silicon. The next one we're going to do is chromium, which is right here. So we're going to do our electron configuration again, which is 1s2, 2s2, 2p6, 3s2, 3p. This time we need to go all the way to the end here, so it's 3p6. Now we're going to come down here. This is our 4s. We need both electrons. And then remember when we're in this section that our n value is n minus 1. So instead of this one being 4, it's actually going to be 3. We're in the D block, but we only need 1, 2, 3, 4 electrons in that. Okay? So now we're going to do our orbital diagrams for this. Again, S gets 1 blank. P gets 3. And then when we get over to the 3D here, we're going to have 5 blanks. Because remember our M values here, we had 5 of them, -2, -1, 0, 1, and 2. So now we're going to put our electrons in, up, down, up, down, up, 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 and then we double up. 1, 2, 3, up, down, up, 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 down, down, down. And these are the plus and the minuses. So plus and minus from your quantum numbers. And then plus, 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 and plus. And we don't double up until there's an electron at each one of these. And then the last one that we're going to work on is bromine. So bromine's electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. So we're down to here now. This is 3d. We need all of these. So it's 3d10. Then after zinc, we go here. This is gallium. Our N number here is 4. We're in the P block, and we need 5 of those electrons. So S gets 1 blank. P's get 3. S's get 1. P's get 3. S's get 1. D's get 5. And P's, again, get 3. So up, down, or plus, minus, plus, minus, plus, 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 minus, 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 plus, minus, plus, 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 minus, 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 plus, minus, plus, 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 and then we go back and fill in our minuses. And then when we get here, we need 5. So 1, 2, 3, 4, 5. And those are our orbital diagrams. Okay. The next thing, or the last thing that we're going to talk about in this chapter, is the electron dot structure. So dots are placed one at a time around the 4 opposite sides of a symbol, and then they're paired until they are all used up. As a side note, we are only looking at elements in the first 2 columns and the last 6 columns. We're going to ignore the D and F block, the transition metals and the intertransition metals. We're not going to do anything with electron dot diagrams for those. So an easy way to remember this is that if you're in this column, you're going to get 1 valence electron. If you're in this one, you have 2. We're going to skip a few here. This is 3, 4, 5, 6, 7, 8. And again, we ignore all of this stuff in between. So calcium is in this first column. So that is 2 valence electrons, right? Ca, do a dot here and a dot here. You could also do a dot here and here. You want to try to get them on opposite sides though. Phosphorus then is the next one. Phosphorus is here. So if we count, we go 1, 2, skip a few, 3, 4, 5. So again, we don't pair up electrons until we have all 4 sides filled. And then that extra electron can go anywhere. I usually put it on the top, but technically it can go anywhere. Selenium is the last one I'm going to show you. There's selenium. So go 1, 2, skip a few, 3, 4, 5, 6. So we need 6 electrons. So 1, 2, 3, 4, 5, and 6. And that's how we do electron dot diagrams. And I've got a few other examples on the next slide as well. Okay.